What specific problem does your method aim to solve in relation to the linear representation hypothesis, LRH, and why is this significant for understanding recurrent neural networks, RNNs?
Our method aims to challenge the strong linear representation hypothesis, LRH, which posits that all concepts in neural networks are represented as linear encodings in distinct subspaces. We present a counterexample using gated recurrent units, GRUS, that demonstrates smaller networks, hidden sizes 48 and 64, utilize onion representations, where sequence positions are identified by magnitude rather than direction, leading to layered features that cannot be isolated in linear subspaces. This finding is significant because it reveals that while larger GRUS can learn linear representations consistent with the LRH, smaller GRUS solve the repeat task through a fundamentally different mechanism, highlighting the limitations of the LRH in fully capturing the representational capabilities of RNNs. By exposing these nonlinear representations, we encourage further exploration of diverse encoding mechanisms in neural networks, which could lead to a deeper understanding of their operational principles.
Could you break down your proposed method step by step? Specifically, explain how the GRUS operate in the context of your onion representation hypothesis, including any novel components introduced in your analysis.
In our analysis of the onion representation hypothesis, we first observe that GRUS process input sequences autoregressively, meaning they generate outputs based on previous inputs. The key novel component of our method is the use of scaling factors to represent token positions through magnitudes rather than directions. Specifically, when replacing a token in the sequence, we compute the difference between the embeddings of the new and old tokens, scaling this difference by a factor determined by the target position. This allows the model to peel back layers of representations, where each layer corresponds to a different position in the sequence, akin to peeling an onion. Finally, we validate the effectiveness of this approach through interventions, demonstrating that the onion representation can achieve significantly higher accuracy in decoding sequences, especially in smaller models where traditional linear representations fail.
Can you provide a detailed example of how the onion representation mechanism works during the repeat task? Walk through a hypothetical sequence and illustrate how the model processes and represents the tokens in this context.
In the context of the repeat task, consider a hypothetical sequence of tokens I_1, I_2, I_3, where each token is represented in the GRU's hidden state vector. As the GRU processes the sequence, it encodes each token's position using a magnitude-based mechanism rather than distinct linear subspaces. For instance, when the model begins generating output at time step t=L+2, it first decodes I_1 by accessing the dominant scale associated with it, which is determined by the magnitude of its embedding. As the model continues to generate tokens, it effectively peels off the representation of I_1 from the hidden state, allowing the next token, I_2, to become the dominant feature in the subsequent time step. This process continues, with the model using the autoregressive feedback to sequentially access and decode each token based on their respective magnitudes, akin to peeling layers of an onion. Thus, the model can represent multiple tokens in the same subspace, with their positions identified by the order of magnitude, enabling it to successfully repeat the entire sequence.
What are the advantages of using onion representations over traditional linear representations in terms of performance and representation capability, particularly for smaller GRU models?
Onion representations offer significant advantages over traditional linear representations, especially for smaller GRU models. N is less than or equal to 64. Firstly, they allow the model to distinguish between a limited number of directions, n_s equals 30, at different orders of magnitude, rather than requiring a unique direction for each position, which is crucial given the limited dimensionality of smaller models. This results in a more efficient encoding of sequence information, enabling the model to achieve 87% accuracy in the repeat task, compared to only 1% accuracy with bigram interventions. Additionally, onion representations leverage the autoregressive nature of GRUS, allowing the model to peel off layers corresponding to different sequence positions, which is not possible with linear representations where each position is independently accessible. This unique capability of onion representations to store multiple features in the same subspace at different scales enhances the representation capacity of smaller models, making them more effective in handling tasks that involve sequential data.
How did you validate the effectiveness of your onion intervention method? And what specific metrics or experimental setups did you use to compare it against other intervention strategies?
To validate the effectiveness of the onion intervention method, we compared its performance against unigram and bigram interventions across various model sizes. Specifically, we measured the accuracy of the onion intervention in replacing tokens within sequences, achieving significantly better results, such as 87% accuracy for the smallest model size n equals 64, compared to only 1% for the bigram intervention. The experimental setup involved using the same training set for the base model and the intervention model, ensuring consistency in evaluation. We also employed a control where we fixed the scaling parameters to assess the impact of the learned scaling factors, which resulted in only 21% accuracy, further highlighting the importance of the dynamic scaling in the onion intervention. This comprehensive comparison across different models and intervention strategies demonstrated the superior effectiveness of the onion intervention in capturing the underlying representations learned by the GRUS.
What results did you find when applying your onion intervention method on different model sizes? And what conclusions can you draw regarding the scalability of your approach and its potential limitations?
When applying the onion intervention method across different model sizes, we found that it achieved significantly better accuracy on smaller models, such as those with a hidden size of 64, reaching 87% accuracy compared to only 1% for the bigram intervention. In contrast, the onion intervention also performed well on larger models, n is greater than or equal to 256, indicating that the method is scalable and can effectively leverage the autoregressive nature of GRUS. However, the performance of the onion intervention on larger models was not as high as on smaller models, suggesting that while it can work on both, the dynamics of gating and representation in larger models may complicate the intervention process. This implies that the onion intervention is particularly well suited for smaller autoregressive models that learn onion representations, but may face limitations in expressing arbitrary gating patterns in larger models. Overall, the results highlight the effectiveness of the onion intervention in capturing the unique representation mechanisms of GRUS, while also indicating potential challenges when scaling to more complex architectures.